Assalamu alaikum everyone. My name is Aliha and the topic that I am going to present today is shape memory alloys. In this presentation, I will cover some main points like what are SMAs, how do they work, their types, unique properties, and manufacturing process, especially focusing on nitinol, which is the most commonly used SMA. So let's start with what are shape memory alloys. Shape memory alloys are a type of smart materials that can return to their original shape after being deformed. When an SMA is heated, it undergoes a transformation that restores its preset shape. These materials can withstand large amount of stress without permanent deformation and can be shaped into wires, plates, bars, and rings for various applications. This ability to remember the shape is what makes them valuable in modern technology. As you can also see in the diagram, the wire is first deformed and returns to its original shape on heating. How do SMAs work? Shape memory alloys function through reversible phase transformations between two phases. The first one is austenite phase, which is stable at high temperature, and the second one is martensite, which forms at low temperature. Martensite phase has two forms. The first one is twinned, which is naturally aligned, and the second one is detwined, which is reoriented by the stress. The transformation between these phases is triggered by heating or cooling and gives SMAs their unique behavior. This solid state transition does not involve any melting or diffusion. Deformation and phase transformation. Let's understand the concept of deformation and phase transformation with the help of diagram. As we can see, when an SMA is cooled from its high temperature austenite phase, it becomes twinned martensite. This transition does not result in any visible shape change because only atomic level changes occur at this stage. However, if the mechanical stress is applied at low temperature, the twinned structure becomes detwined martensite, visibly deforming the material. The deformation remains until the SMA is reheated, triggering a reverse transformation back to austenite and recovering its original shape. Shape memory effect and recovery. The shape memory effect is observed when a deformed shape memory alloy regains its original shape upon heating above a critical temperature known as austenite finish temperature, which is represented by AF. This is possible because the material was strained in the austenite phase. Once the desired shape is formed in that phase, it can be cooled and later heated to regain it. This effect is what makes SMAs useful in many actuations and biomedical applications. Types of SMAs. Basically, there are two main families of SMAs. The first one is copper-based alloys and the second one is nickel-based alloys. Copper-based alloys include copper, aluminium, nickel, and copper, zinc, aluminium alloys. On the other hand, nickel-based alloys include nickel and titanium-based alloys. Copper-based shape memory alloys are more cost effective but have lower fatigue resistance. It means they cannot bear the repeated pressure or load. On the other hand, nickel and titanium based alloys, especially nitinol, dominates over 90% of the current shape memory alloy applications because they offer superior corrosion resistance, biocompatibility, and better electrical resistance, which is crucial for heating based actuations. Unique properties of shape memory alloys. Shape memory alloys exhibit two main properties. The first one is shape memory effect, and the second one is elasticity, superelasticity effect. The shape memory effect arises from the diffusion-less transformation between austenite and martensite. This transformation can be triggered either by the stress or temperature changes. Superelasticity allows the shape memory alloys to undergo large strains and can still return to its original shape when the load is removed, especially when the material operates above the transformation temperature. Now let's discuss the shape memory effect behavior. There are basically two types of shape memory effect behaviors. In one way shape memory effect, the material returns to its original shape only when heated. Further heating or cooling do not affect the shape, as you can see in the diagram. On the other hand, in two-way shape memory alloys, the material remembers one shape during heating and a different shape during cooling. The two-way effect is more complex and usually requires more extensive training and cycling during processing. Moving on to the second property, which is superelasticity. Superelasticity is a property that allows shape memory alloys to stretch and then recover without permanent deformation when the load is removed. This happens at a temperature above the transition range. As stress is increased, the material transforms from austenite to martensite. When the load is removed, the martensite quickly reverts back to austenite, enabling the material to return to its original form without needing heat. Superelasticity allows the shape memory alloys to beat the stretching deformation up to 10 to 8%. Let's understand this concept with the help of diagram. As you can see in the diagram, the SMA begins in austenite phase, which is strong and rigid. As you apply the stress, the material starts to deform elasticity. Like any metal, as the stress is increased beyond a certain point, the material begins to transform from austenite to martensite phase. It means that the material deforms more without needing much extra force. At further loading, the material is now fully in martensite phase and continues to deform just like a regular metal. When the load is removed, the material starts transforming back into the austenite phase. The further unloading, SMS returns to original shape without needing heat. By the time you reach at the end of unloading curve, the material is fully austenitic again and has recovered its original shape. Nitinol. Nitinol is basically the most commonly used shape memory alloy. It is made up of nickel and titanium. It displays both shape memory effect and superelasticity due to the reversible diffusionless phase changes. The austenite phase has a high temperature cubic structure B2 and the martensite phase has a low temperature monoclinic structure B19. These phase changes occur through the lattice distortion, not atomic diffusion or bond breaking, making them fast and reliable. Manufacturing of nitinol. The first step in the manufacturing of nitinol is alloy formation, in which nitinol is made by melting the pure nickel and titanium in a vacuum or inert gas atmosphere at around 1310 degrees Celsius temperature. The basic reaction involves the addition of equal proportions of nickel and titanium, which form austenite phase of nitinol. Maintenance of 1:1 atomic ratio is essential. Any deviation can result in the brittle phases such as trinickel titanium if the nickel is in excess, or nickel dititanide if the titanium is in excess, which negatively affects the performance and stability of the alloys. Phase transformation. The second step in the manufacturing of nitinol is phase transformation. During cooling or under mechanical stress, nitinol transforms from austenite to martensite phase, a process known as forward transformation. This is a lattice level rearrangement without atomic diffusion, enabling quick and reversible phase change. In sum, nickel-rich alloys, an intermediate R phase may form between austenite and martensite phase, affecting the hysteresis and mechanical properties. Shape change mechanism. The third step in the manufacturing of nitinol is shape change mechanism. When the stress is applied to twined martensite at low temperature, it becomes detwined, as we have already discussed in the previous slides, leading to deformation. When heated above AF, the ditwined martensite reverts back to austenite, restoring the original shape. This is the shape memory effect. At high temperatures, stress alone can cause the austenite to transform into martensite. There is no need to apply any load, and once the stress is removed, it changes back. This is the basis for superelastic behavior, allowing strain recovery up to 8 to 10%. Aging and precipitations. The last step of nitinol manufacturing is aging and precipitation. Aging is a type of treatment. In nickel-rich nitinol, aging occurs at 300 to 500 degrees Celsius, which leads to the formation of tetra-nickel trititanide precipitates. In this reaction, nitinol is converted into tetra-nickel trititanide and nitinol matrix. These precipitates enhance the material's mechanical performance by fine-tuning transformation temperatures like MS and AF, like known as martensite starting temperature and austenite finishing temperature, blocking dislocations and improving the fatigue life. It means they can bear more load. This aging process allows engineers to customize the behavior of nitinol for specific uses in medicines, aerospace, and robotics. Thank you so much. That's all was from my side. We'll continue the second part of this presentation in the next video.